So in section 5.3, we're introduced to an idea called independence. Two events are independent if they don't affect each other. So for example, coin flips. The outcome of one coin flip certainly doesn't have any effect on the outcome of the next coin flip, which is kind of interesting if you think about what this means. If you get a sequence of heads and tails and say you flip a coin 8 times in a row and you happened to get 8 heads, that means on your 9th flip, the probability of heads is still 1/2. Doesn't matter that you got 8 heads in a row, which is unlikely, but if that did happen, the probability of heads on your 9th flip is completely independent of those 8 heads in a row happening before it. On the 9th flip, the probability of heads is still just 1/2, and the probability of tails is still just 1/2. Coin flips are independent. The outcome of one flip doesn't affect the outcome of the next flip. Another independent set of events are if we're drawing cards. Specifically, if we're drawing cards, what we call with replacement, meaning we put back a card before we draw the next one, then whatever we drew the first time, by the time we draw the second card, the first card's outcome, whether it was a king or 7 or whatever, doesn't affect the second card that we draw. Which seems obvious. That's what independence is. Another example of independent events that we'll use are rolling dice. Oh, I got a 3 with that die. Well, it's time to roll the next die. The outcome of this die is not going to depend at all on the fact that my first die was a 3. Let's look at the definition from the book. The book's definition of independence talks about two events, which they're calling E and F here. They're independent if the occurrence of event E, the probability of F, isn't affected by that. So let's look at an example drawing a card, a single card from a deck. And I'm going to define 3 events here. And we could wonder, are these events independent from one another? The way I like to think about it is similar to how we talked about conditional probabilities. Here you are, and you are a stat wizard, and you love to think about the probabilities of events. And here you are thinking about the probability that the card is a king. Right now, you would think that, hey, the probability that my next card is a king is going to be 4 over 52 because there's 4 kings in a deck of 52 cards. Let's enroll the help of our trusty card-loving friend here who is going to tell us something about the card without showing us the card. And he's going to, or she, is going to tell us that the card is red. They've basically told us that event R happened. So we want to know, what's the probability of K now? Did the fact that the card is red affect the probability that the card is a king? Now I know that there are only 26 red cards, and 2 of those cards are kings. So this was my before probability, before I knew that event R happened. This is my after probability. But if you notice, these 2 things are the same. Both these probabilities are actually the same number, kind of in disguise. And so event R happening didn't change the probability that the card is a king. The event R and K are independent. Knowing that the card is red didn't change the probability that the card was a king at all. So let's look at another situation. There you are, you're still wondering, hey, what's the probability that I get a king? Who knows, maybe you're playing poker and you have a king and you want another king. Being the discerning stat student that you are, you know the probability is 4 out of 52. Now you have your helpful friend look at this card and say that this card is a face card. So now you say, okay, the probability that it's a king is no longer 4 out of 52. Gotta increase my thought bubble here. I'm thinking a lot of thoughts. There's 4 kings out of the 16 face cards. So the probability that it's a king, if somebody told me it was a face card, is 4 out of 16. And these are definitely not the same probability. The probability is quite a bit higher if I know that it's a face card. So what does that mean? It means that the events F and K are not independent. I definitely learned some useful information in terms of my ability to guess this card if I was told that that card was a face card. The events F and K do affect each other. The probability of K depends on whether or not F happened. I've mentioned that the before probability is an unconditional probability and this after probability is a conditional probability, which means that we've discovered a rule for independence here. If I have two events that are independent, the unconditional probability of A is the same as the probability of A given that B happens. It doesn't matter whether or not B happened. The probability of A is still the same. Loosely speaking, independence means that the events don't affect each other. But in terms of conditional probabilities, if two events are independent, then the unconditional probability of one is the same as the probability of that event conditioned on the other event. To summarize what we just saw, the events R and K are independent because knowing that the card is red doesn't affect that the card is a king. The probability that the card is a king unconditionally is the same thing as the probability that the card is a king if I know the card is red. And actually that goes the other way too. The probability that the card is red unconditionally is the same thing as the probability that the card is red given that I know the card is a king. These events are definitely independent. They do not affect each other. And then the events F and K are not independent. They definitely affect each other. The probability that the card is a king is not the same as the probability that the card is a king given the card is a face card. And likewise, the probability that the card is a face card is definitely not the same as the probability that the card is a face card given it's a king. What is this probability? Well, the probability it's a face card given it's a king is 1. It is certain. There is no way you're going to get a king that isn't a face card. So F and K are not independent. Independence is a really important idea. Whether the outcome of one event affects the other event determines how we can find the probability of multiple events. Sometimes those events influence each other and sometimes they don't. And we have mathematical ways to talk about that. I hope that helps. Thank you for watching.